This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, welcome back. As I said last lecture, we've now got through the core of our theory. The next couple of lectures are all about applying it to the different standard cycles. Standard means for a particular engine type. If we represent each of the processes by its most idealized version that still captures the idea, can we do an analysis on that engine? So our journey will be to have a look at the two car engine cycles, the Otto cycle and the diesel cycle. The Otto cycle is a gasoline engine cycle. The gas turbine cycle, which is called the Brayton cycle. And two of our main vapor cycles, which are the steam cycle and the refrigerator. So today we'll have enough time to go through two of those. And I've said a couple of times that my categorization for thermo, or the categorization for the tools that we build up, split into sections. You have similar tools for achieving the same end that are split up into, are we a closed cycle or an open cycle? They split up into, are we a vapor, which is to say, am I using steam tables, or am I an ideal gas? The first cycles we're going to look at are two of the ideal gas cycles. I don't want to race up and tell them to be quiet, but if anyone's got a lot of character about them, could you just stick your head about and say shh? If no one's got any character about them, that's okay if you just sit there and see whether they quieten down. So that's the main division. We're going to look today at two of the air standard cycles. Aha, it's all right, one person's already going. It's okay, one person's already going. Oh no, they've just closed the door rather than have a confrontation. It's a solution. The main thing we'll do, as we introduce each cycle, the main thing we're going to do is work towards a statement of the ideal efficiency. It looks like a relatively small, simple goal. For all the things that we could talk about in an engine, to just look at the efficiency looks like a small target. But in doing so, we need to completely describe the cycle and look at all of the processes. So that's what we're going to do. We'll do the Otto first. Now, the Otto cycle is a car cycle. It's a car engine cycle, and it's a car engine cycle for a spark ignition engine, which is to say a normal gasoline or petrol engine. I always get caught out by one slide. But before we get on to the Otto cycle, I want to draw your attention to some more thermodynamic code words. In this case, the thermodynamic code word is the air standard cycle. There are two sets of code words around the air standard cycle. One is air standard cycle, and the other is cold air standard cycle. So when we get to the gas turbine engine, we'll look at the cold air standard, but for today we'll look at the air standard cycle. The first assumption is nice and simple. We're using air as the working fluid, which means I'm using an ideal gas as the working fluid, which gives you access to all of the ideal gas equations that we've built up so far. The moment that I say I'm using air, opens up this set of solutions and this set of tools. In the air standard cycles, any heat transfer from combustion, I'm not analysing. I'm not solving for the release of energy from burning something. I'm not solving for, importantly, I'm not solving for any mass transfer of fuel into my problem, even though one can later on solve for this. So the air standard cycle is saying whatever heat I get from burning something is just a Q, or a Q dot. It's just a heat transfer. The air standard cycle has the air going through a closed cycle and being returned to its original state by some heat rejection back out to the outside world. Setting up those rules let's just focus on the simple analytic equations that we've built up so far. My notes are really, really, really different to what I printed out. My apologies. If I look a little disconnected, it's because this set is different to this set. I am happy to talk about gas turbine engines or Otto cycle engines like this, and so that's what you'll see. I'm going to go as per what I'm flashing up on the screen. So the gas turbine cycle, before I get to the Otto cycle, it's one of those Friday days. The gas turbine cycle does what almost all heat engines do. It takes some air, squeezes it, heats it up, gets some power out of it, and lets it go again. The old sentence that used to get added to this is suck, squeeze, bang, blow, which is to say, coming in the front comes the air, compress it down, squeeze, bang, set fire to something, add heaps of energy, and out the end, blow. The components that let us do that are a compressor, a combustion chamber, a turbine, and the exhaust. So if the air is flowing this way through that gas turbine, I'm indicating from the left to the right if you're watching this at home. If the air is flowing this way through my gas turbine, it gets compressed, gets heat added, expands. In the process, I have to put work in through the compressor, and I get work out from the turbine. There are two ways I can run a gas turbine engine. One is to produce work, like shaft work, and the other is as propulsion, as my aircraft engine. When I'm producing shaft work, the turbine is producing more output than the compressor, and so my net system work is positive out. When I'm running it as propulsion, the turbine exactly just powers the compressor. The extra energy that I've released comes out as thrust, and we'll do that in about 2 lectures' time, very briefly. We've already seen from as we started to play with entropy that compression and expansion, the best possible compression expansion that I can have as a process is isentropic. During my heat addition, by design, I try not to lose any pressure at all. So in the combustion chamber of a gas turbine, which is a constant flow process, I try to keep that pressure exactly as high as what came out of the compressor. And so the most idealized process I can have for that is a constant pressure Q dot. So on my TS diagram, here's my TS diagram, I've got isentropic compression, a line of constant pressure over which I have Q in. So I should be at a hotter temperature by the end of that. Isentropic expansion, where I've got work coming out, and then I reject some heat to the outside world at a constant pressure. Imagine the exhaust of a gas turbine comes out to the outside world, which means it's already at atmospheric pressure. And so this line usually is the pressure of the outside world. I can draw that on a PV diagram. So in this case, the area under the lines is my heat transfer. On a PV diagram, that's my entropy constant line. This is my constant pressure heat addition. That's my entropy constant line, and this is my constant pressure heat rejection. I know I've shown you a GT before, but I like pictures of GTs. It's just a thing about me. I find them very elegant, and I find them interesting to have a look at, particularly with a view to how small is the combustion chamber compared to the rest of the process. This is an industrial gas turbine, which is to say it's a gas turbine that's designed for producing electrical power or driving a generator to make electricity. This is an aviation gas turbine. Its primary job is to make thrust, to push air out the back with high momentum than what came in the front. And most modern GTs have a great big fan out the front, effectively a propeller, and the gas turbine just takes part of that air. So if we compare the yellow bit here and everything from here to here, these are the compressor stages. My compressed air then bends around and comes down through here, and I put my fuel in and set fire to it here. And this is an annulus all the way around the GT. In this guy, the red section, sorry, not the red section, these are compressors, This guy here is where the combustion's happening, again as an annulus. And then I've got turbine, turbine. Here I've got turbine, turbine, turbine. I usually have many more compressor stages than I do turbine stages. But for the thermoanalysis, we treat them as one thing. Even though the compressor is made up of many, many, many fans, squeezing the air down and down and down and down, we treat it as one thing for now. And the turbine we treat as one thing as well. What I'm about to put on the screen is the words of what I've just been describing to you, so I'll get them up on the screen. We're dealing with the idealized cases. So, air comes in, compressed. High pressure, high temperature at the end of that job. It means high enthalpy, isentropic compression. You get there by shaft work in. Fuel air mixing, ignited. For a gas turbine, that's a constant, there's no ongoing spark. Once the flame is established, you have a constant flow of mass through that chamber that just keeps burning and burning and burning. They just keep putting fuel into it. That raises the temperature but not the pressure, and then through the turbine, and then the shaft work from the turbine drives the compressor as well as any extra work you want done. So let's do a little bit of analysis on that. This guy is usually called the Brayton cycle. Now, do I need to remember whether it's called what the Brayton cycle is? I'm going to say yes. It's one of the few times where I wave at words and say, yes, it's important for you to know this. By the end of your 6 weeks, it is important for you to know what an Otto cycle is and what its main components are. It's important for you to know what a Brayton cycle is and what its main components are. When we get to the steam turbine coal-fired power generation system, it's important for you to know what a Rankine cycle is and what its main components are. This will be one of your jobs by the end of this 6 weeks. So if I were to say, sketch an Otto cycle, sketch a Brayton cycle on a TS diagram, you should be able to do this without going, sorry, I don't know what that is. Air standard assumptions, as I just said, and we make every process as ideal as it can be. So you remember when we did a Carnot cycle, the Carnot cycle on the TS diagram was a box. It was a square, it was a rectangular box with parallel sides, isentropic processes here, isothermal processes here. This guy has isentropic processes for the compression and expansion, but it has constant pressure processes for the heat addition and heat rejection. So these are the diagrams I've already walked through. And as I said, our main objective will be to write down an expression for the ideal Brayton cycle efficiency. So we have an expression already for the Carnot efficiency, which is say this will operate between the flame temperature and the outside world temperature, so I know it's Carnot efficiency. But now that I put in these constant pressure processes instead of isothermal processes, I will have a different number, which will be the best possible gas turbine efficiency between those temperatures. So let's have a look at how that looks. Efficiency shouldn't be a mystery. Just get a piece of paper up on the screen. Efficiency is net work over the heat input. So if I've got, I'm writing now thermal efficiency because very soon we're going to have the idea of isentropic efficiency, two different concepts. So for the moment I'm specifying thermal efficiency, which is to say net work divided by heat output. Can we see this? Yes. Ouch. Better? Yes. So, workout, I'm referring to net work, which is to say the turbine work minus the compressor work. Turbine work should be bigger than the compressor work. For the compressor work and the turbine work, I'd like to write some nice simple equations for those. If I go Q minus W shaft equals, is this a steady flow or a closed problem with steady mass? Steady flow problem. And so this statement becomes m dot delta H plus delta KE plus delta PE. And if I get rid of my mass flows, which is to say get rid of this and this, make a little w, little q, and also make the assumption of not really changing the velocity through the system and not really changing the height of the system during my analysis, during my cycle. And I've said that this is the best that I can make it. One of the ways that I make things good is not letting go of any energy on the way, which is to say getting rid of heat loss, insulating the thing. This is for the compressor and the turbine. Remember on the TS diagram, we drew these guys as compressor and turbine. No heat transfer under a straight vertical line. So what I've now got is work compressor and work turbine equals delta H equals delta H. And I told you that we were working with an ideal gas. So instead of delta H, what can I use? CP delta T. Why not CV delta T? Someone? Both of them rely on the so CP and CV delta T both rely on delta T. So why can't I use CV delta T? That's it. The answer there was because it's enthalpy. CP connects temperature and enthalpy. CV connects temperature and internal energy. So it's an ideal gas, so I can write these down as C something delta T, and the C is because I'm doing enthalpy. My C is CP T2 minus T1 for the compressor, and CP T3 minus T4. 1, 2, 3, 4 for the turbine. Depends on how you put your minus sign. The work that comes out of this guy will be the high temperature minus the low temperature. For the moment, just as I'm writing them down, the work that goes into the compressor will be this minus this. So this number, if I write this number as a positive and this number as a positive, when I put them in here, I'll get a big number minus a small number, and it functions. It's shorthand by me because I'm accustomed to it, but it is worth paying attention to which way you expect the work to be going. And then my Q in is again delta H over the combustion chamber, which is again a CP T3 minus T2. This guy. So, all the way through there, I've got an expression in terms of CP delta T, which means that when it comes time for me to write down the enthalpy, my goodness, the efficiency, I'm expecting probably all those CPs are going to cancel out. If I can express all of my works in terms of temperature and CP, and all of my heat transfers in terms of temperature and CP, the CPs are all going to pop out, and I'm going to have an expression in terms just of temperature. We need one extra trick. To make this work, I need to know one extra trick. If I need a way to connect my temperature over an isentropic process. So, if you take your time with the isentropic process equations, you can get to this, and we'll try to show it later. I have the relationship that T2 on T1 equals Rp gamma minus 1 on gamma. You look at it and go, I've never proven that. I've never shown that. We will get there. What is RP? This is the pressure ratio between this pressure and this pressure. So which is to say, if this pressure were atmospheric and this guy was 30, that pressure ratio would be 30 divided by 1, 30. So it's the pressure ratio. This RP defines a gas turbine. We will find, as we go on, we will find that there are terms that define each major cycle. In a gas turbine, it's RP. Each major air cycle. There's a term that defines gas turbine, there's a term that defines Otto cycle, and a term that defines the diesel cycle. What's happened here is that through the isentropic, I can determine this guy. If you remember, I had the PV to the gamma equals a constant equations, and I've got PV equals RT as well. With a combination of those two and some substitutions, you can develop an expression for how does temperature change with pressure at a constant entropy. We've also got that S2 minus S1 equation. I wave my hand at this for now to say we will derive this. For the sake of this exercise, let's keep going, and then we'll come back to it. What I now have is that my thermal efficiency, if I express this, hang on, let me take a couple of steps. If I express this as Cp T3 minus T4 minus Cp T2 minus T1, this is turbine minus compressor, over Cp T3 minus T2, and I cross out all my Cp's, I now have a pretty messy expression in terms of T. And what I need are ways to substitute in here that allow me to break this down to a much, much simpler equation. If I had all my temperatures, I could just plug that in. But I want an even neater expression. I want an expression that I can say in terms of the properties of the gas turbine. So if I define a gas turbine for you in terms of the major thing it does, compressing and expanding. So if I define the gas turbine for you in terms of its compression ratio, sorry, its pressure ratio, I should be able to pop that into an equation that gives me the efficiency rather than having to go through and calculate the temperature at each point. So what we then do is I'm going to factor out, from here, I'm going to factor out my T3 and leave myself with 1 minus T4 and T3. From here, I'm going to factor out a T3 as well. No, a T2, and leave myself with 1 minus T1 on T2. And from here, I'm going to leave that as is for now. Why would I do that? Because if I take a T3 out of this and a T2 out of this, I've got a T3 and T2 at the bottom. So if I can factor out a T3 and a T2 from this guy, I can get rid of those terms. My job gets simpler and simpler. So let's do that. T3, 1 minus. Now, if I start using this guy, I can say that this T2 on T1 is this. I can also say that T3 on T4 equals this. If you take your time to do it, one can do this. So now what I've got, T3, 1 minus RP, 1 minus gamma on gamma. I feel like I probably need more paper here. Minus T2, 1 minus RP, 1 minus gamma on gamma. Big brackets, over T3 minus T2. This term and this term are the same, so I can pull them out. I've got T3 minus T2 times 1 minus RP, 1 minus gamma on the gamma, which means my T3 and T2 can cancel out. This will take me to 1 minus RP, 1 minus gamma on the gamma. It is also possible, also equals 1 minus 1 over RP, gamma minus 1 on gamma. So, you see me scribble those things down and you nod and smile. Because I've done this a lot. I can write it on paper. My objective here is to have written on paper and said it out aloud so that when you come back to it and try to do it 3 or 4 times, you have the information available to you to solve it again. So I'm not necessarily expecting you to magically grab it the first time you see it, because there's actually a little bit of maths in here that is worth proving to yourself that you can do. Let's get this back up on screen so it's not just my scribbly handwriting. So this is everything that I've just scribbled on the piece of paper, having it up on screen so that it's there for you. And then going through each of those steps. So now it's printed nicely so you don't have to follow my scrawled handwriting that's mashed up on a document capture. What that last expression means is that my efficiency for a gas turbine engine is absolutely defined the moment that I choose a working fluid, air, and the moment that I choose a pressure ratio. So if I want my efficiency to go up, I need to increase my pressure of the compressor. I need a bigger compressor. So I get the world's biggest compressor and I put pressure up to infinity. What happens to my temperature? Every time I compress, my temperature goes up. If I set fire to something then on top of that compressed air, it will get hotter and hotter. So there will be a natural limit to how big I can make these things, and that natural limit is once I've compressed and then set fire to my fuel, that final temperature better not melt the engine. So there's a limit, there's a practical limit to my compression ratios. But if I had absolute liberty to define whatever pressure ratio I want, I can actually map efficiency in terms of pressure ratio and have a look at where we lie. Compression ratio of 10 takes me up to about 45% for an ideal process. We're sitting around 42% or so on a once-through gas turbine engine at compression ratios of around 35, which means that my best possible efficiencies are still a little bit lower than the ideal. My best possible practical efficiencies are a little bit lower than the ideal here. If I were to do a propulsion cycle, my objective is to get velocity out the end and to take an incoming, imagine I'm flying. I need my gas to slow down a bit, so I have a little diffuser that slows my gas down. It comes into the compressor, and that's because I'm flying at about 900 kilometers an hour. So I actually want to slow the gas down a little bit, run it through my compressor, squeeze it up together. I get a little boost through, if you do the maths of a diffuser, which you will need to do during your tutorials, you do the maths of a tutorial, if you do the maths of a diffuser, you end up with an enthalpy increase. You end up with a temperature increase. So I've turned kinetic energy into enthalpy and into temperature. So diffuser, and then a compressor, and then I add in my fire, then I've got my turbine, and then I give a little squeeze on its way out to increase its velocity again. I've got all this extra temperature that I can turn back into velocity. And so I have a nozzle at the end. This guy, his job is to use all of the turbine power only to run the compressor. And the excess temperature, so now I don't take my turbine all the way down, so I'm waving my hands now. I'm waving my hands from a hot temperature to atmospheric, cold temperature. Instead, I use my turbine just far enough to run the compressor, and the enthalpy I've got left over, the heat that I've got left over, I turn into velocity. I turn into kinetic energy. So that's the point of that last nozzle. So that's how a gas turbine flies. That's how it provides thrust. I need a difference between the momentum coming in and the momentum going out, which comes from even at a constant mass flow rate, that only comes from a delta V. So I shouldn't have tapped as I was making that last point. This last row of equations I will, if you've already seen the equation sheet I give to you in the exams, but you need to know when and how to use them. On an isentropic process for an ideal gas, these all work. They work by doing a combination of things. They work by taking your isentropic relationships, which we built up last lecture, as well as your ideal gas, as well as your PV to the gamma, put them all together, and you end up with the isentropic ideal gas relationships. One connects temperature to specific volume, one connects temperature to pressure, and then you can, of course, connect pressure to specific volume. All right, let's go on to the Otto cycle. The Otto cycle, the gasoline engine cycle, or the spark ignition cycle. If you've not by now come across a car engine, if you've not come across the cycle that it goes on, standard 4-stroke cycle. So I've got a piston going up and down in a cylinder. You can have 2 strokes giving me my entire power cycle, which is say compress, bang, expand, work done, work released. Or I can have 4 strokes defining my power cycle, which is to say suck in my air, compress it, bang, exhaust it. So that's what's referred to as a 4-stroke cycle. 1, 2, 3, 4. On one of the strokes, squeeze, that's my work in. Bang, that's my work out. And then a heat rejection, out again. If we map these out, I'm operating, there are a couple of new terms, and they're terms that it's time that if you've never heard of them, that you hear of them. When describing engines, you can describe top dead center and bottom dead center. Because this is because you've got a rotating piece of machinery pushing a piston up and down, usually up and down, when it's all the way up at the top, that's referred to as top dead center, or TDC here. When it's all the way down at the bottom, that's referred bottom dead center, or BDC here. And that defines what's referred to as the swept volume, which is when you describe the volume of a car. If you say that's a 350cc car, or this is a 3-litre car, or a 5-litre car, or a 1-litre car, that's the volume that's being referred to, the displaced volume of all the pistons in the engine. So, to control that process, I let air in and I let air out through some gates called valves. The air comes in through the intake valve and it goes out through the exhaust valve, so no mystery. Intake, out it goes. But first, I squeeze it up. I've put the fuel in already. So I take the air in, I squeeze up the air, I put the fuel in, and then set fire to it with a spark. That flame goes bang. Hopefully it doesn't explode, but it burns through the combustion chamber. And then now that I've got hot, high-pressure gas, I let it push the cylinder back down again. That's the expansion stroke. So intake, compression, expansion, exhaust. On my way back up, I use the momentum of the engine as it's pushing around to push the air back out again and then get ready for the next cycle. It's a closed, we treat the power part of this cycle. The compression and expansion are the bit that we mostly concern ourselves with, because they're the bit where I really have to push and I really get my work out. During those two processes, my valves are closed, which is to say this is now effectively a closed system. No mass crossing the boundary. I'm going to ignore the fuel mass for now, because I'm treating that as a heat addition, as a Q dot, rather than a mass addition. And so, because it's a closed system, the main thing I'm concerned about is keeping track of the internal energy, not of the enthalpy. So I draw it on a PV diagram. If I do any ideal gas equations, I'm going to be using CV delta T, not CP delta T. And my major process is starting from bottom dead center. So I'm going to come back. Starting from here, I push up. So starting from some low pressure, big volume, I squeeze up to some small volume and a higher pressure. I then put the fuel in and set fire to it while not changing the volume. So I'm going to refer to that as a constant volume process. I'm going to assume that all my fuel is burnt, so all my heat is released during that process. And so if I keep the volume constant and I increase the temperature, my pressure will go up. So constant volume heat addition, boom. And then I let the thing expand. And down it comes. This compression and expansion, the best possible compression and expansion I can do is isentropic, which is to say adiabatic and reversible. So these are isentropic compression, isentropic expansion. So if they were on a TS diagram, they'd be isentropic compression and isentropic expansion. We've just looked at constant pressure lines on a TS diagram. The constant volume lines take me to a higher temperature. So with the same heat addition, that's my constant pressure line, that's my constant volume line. Constant volume, isentropic, constant volume, isentropic. That's my Otto cycle for a thermodynamicist. For you guys, for now. It doesn't tell you anything about the spark, it doesn't tell you anything about the energy content of petrol versus diesel, and it doesn't map it out over a whole car engine trying to provide some kilowatts to the wheels. We're just talking about the power cycle of boom, boom. And then we let it go free to take the air in and out. Those little free inlet and exhausts are these guys here. So the piston travels its whole volume from bottom dead center to top dead center during the exhaust and intake process. So it goes push everything out. It's constant pressure because I open up a valve to the outside world. So suddenly everything is at atmospheric pressure, approximately. So at atmospheric pressure, I open up a valve to the outside world, I push all the air out, and I draw in new air, ready to start again. Now this process does basically nothing, and so more often than not we ignore it for the analysis of the Otto cycle. Okay. We'll play the same game, which is to say let's get an expression for the efficiency. This time, the energy counter that I'm using, as I said before, the energy counter I'm using for a closed problem is internal energy. And so if I'm using internal energy, then I get to use CV delta T, not CP delta T. That's your job to remember. Starting from my definition for efficiency, I'm just trying to decide whether to do it on document cam or not. It seems to settle in better if I do it on doc cam. So let's do that. Let's do that. The idea that I'm going to introduce here, the goal for this will be to show an expression that looks like this. Thermal efficiency of an Otto cycle is going to look like 1 minus 1 over V gamma minus 1. That looks very similar to what we did for the Brayton cycle. The differences are the R that I'm using there is a volume ratio, not a pressure ratio. And it's referred to as the compression ratio of the engine as opposed to the pressure ratio of the gas turbine. And the form of it is gamma minus 1 instead of gamma minus 1 on gamma. We'll get there in a very much similar way, which is to say that the thermal efficiency is net work over Q in, and that this guy can be written as either work in minus work out, or Q in minus Q out. Because I've got nice processes for the heat transfer, which is to say constant volume processes for the heat transfer, it's actually easier for me to solve this problem with Q in minus Q out with a delta Q for network. Remember, it's a closed cycle, so my network has to equal my net heat transfer. So up here, I can write Q 2, 3. There's no point me writing 2, 3 if I haven't drawn a cycle. P, V, 1, 2, 3, 4. This is Q in. This is Q out. Okay? So Q 2, 3 minus Q 4, 1 over Q 2, 3. And if I use my ideal gas law that I've got mCV T3 minus T2 minus T4 minus T1 over mCV T3 minus T2. Obviously I can get rid of these guys. This cancels nicely, so what I'm left with is 1 minus T4 minus T1 and T3 minus T2. Which is not yet in the form that I would like to have it. I'd like to have this in a form where I can analytically evaluate the efficiency of an Otto cycle without knowing what temperature was operating between. Just by giving me information about the geometry of the Otto cycle, which is to say the volume ratio of the piston. So I'm not there yet. What I'm going to use is one of these other processes. So P2 on P1 equals V1 on V2 to the gamma, and also T2 on T1 equals V1 on V2 to the gamma minus 1. And this guy is also the same as T3 on T4. This will be our saviour. So what we're going to do up here is divide through by T1 and divide through by T2. So what I'll be left with is 1 minus T1, T4 on T1 minus 1 over T2, T3 on T2 minus 1. Almost there, just before the magic trick. This is RV. I've got an expression for T2 on T1, which is this. I've got an expression for T3 on T4. In here, I've got T4 on T1 and T3 on T2. Now, what do I know about T4 on T1 and T3 on T2? What I've got, T4 on T1 equals T3 on T2. As a result, this term vanishes, which means that my efficiency becomes 1 minus this guy. So what we're substituting here, if this is RV, then what I've got is 1 over RV gamma minus 1. This step, I want you to convince yourself of. Because if you were asked to derive the expression for the efficiency of an ideal gas Otto cycle in an exam or a mid-sem, you need to know what's the magic trick and can I do it? Can I write it down? So what's the magic trick on a Brayton cycle? What's the magic trick on an Otto cycle, on a diesel cycle? Yep.
Should we use gamma only for adiabatic processes?
No. Gamma is gamma is a constant. As soon as you choose the working fluid, gamma exists. There are times when you need gamma in your solution, and so once you've defined the working fluid, whenever you need the gamma, you use it. The gamma is referred to as the adiabatic constant. because in the PV to the gamma equals a constant, it's the gamma that appears there. It's Cp divided by Cv. So it also appears there. You will find the place where gamma turns up in our equations will be because of when we've had to look at an adiabatic process. And the places in these that we look at adiabatic processes are the isentropic processes because they're adiabatic and reversible. Okay? So that's where the terms pop up, and once they're in, so now I express the efficiency of the whole cycle, which includes non-adiabatic processes. But I've got a gamma term in there because of all the derivation that's crossed things off. Okay? Okay. This is all the things we've just done, written down neatly rather than by my scribble. All the way through to what we just concluded. So this is for the purposes of having it in the notes, written down nicely. In the same way as we could vary the compression ratio, the pressure ratio of a gas turbine, we could vary the compression ratio of a car engine. Car engine compression ratios tend to be, this is a bit where it used to be that everyone knew this, and now most people don't. So they sit around here. We will find later on that diesel engine compression ratios sit up around here. That's the whole point. Diesel is harder to auto-ignite. The thing that stops you from having a bigger and bigger compression ratio is as you squeeze up, you get hotter, and gasoline likes to burn, and particularly it likes to auto-ignite. And that auto-ignition is referred to as knock because it goes bang before you are ready for it. If your flame burns before you're ready for it, it means it's while I'm still trying to push up against it, it catches fire. And so now my car engine shudders to a halt because it's trying to fight up against this massive pressure release. So I don't want that to happen. I want the combustion to be nice and controlled after I've hit top dead center, to happen almost entirely at that constant volume. Bang now, but not an explosion, and not an auto-ignition, a burning flame front, and then release that energy through the pressure. So knock, this pre-ignition, this auto-ignition, knock will destroy an engine and make it undrivable. And so when you're putting your fuel into your engine and it's got a 91 or a 95 or a 98, these are referring to how resistant these fuels are to auto-igniting, to going bang. The higher the number, the more resistant they are, which means the harder I can squeeze them before they catch fire. So if I can squeeze them harder, I can get more efficiency out of my engine. So if I design my engine to squeeze harder, I better make sure that I match it with the right fuel. If I put a 91 fuel into a 98 capable engine, it's still going to try to squeeze all that way, but the fuel I've put in is going to go bang beforehand. So if you've got a cheap car, it doesn't matter if you put expensive fuel into it, because it's just that the fuel had extra potential you're never going to unlock. If you've got an expensive car and you put cheap fuel in it, you destroy the engine. So pay attention. One day you might have expensive cars. All right. We will do similar exercises for our other cycles. Some of the cycles are easier to analyse than others. But be prepared for that kind of thinking. And then once we've done that, we'll do some worked examples as well. So we'll do the diesel to complete the air cycles, and then we'll move on to Rankine and a little bit more Brayton, and then we'll do the refrigeration and heat pump cycles. The exam will cover thermodynamics. The exam happens after all of our thermodynamic lectures. I'm going to actually, just before I lose you all, I'm going to make one point. A couple of questions have come up to me already about tutorials and tutorial solutions. This is not a passive learning exercise. You have tutors and you have me, and we are here to help you learn. If you're doing tutorial problems and you get stuck, if you've found a concept you don't understand, it is okay for you to email your tutors with some working. It is okay for you to take a photo of your working and send it to me or your tutors and say, I'm stuck, can you help me out? We've seen the most common errors in almost all of these questions 1,000 times. So when you're stuck, it may take only 5 minutes of our time to quickly get you back on track again. If the email comes in the middle of the night, you may have to wait till morning. But use your tutor, which is to say work out who your tutor's name is first. Use your tutor and you can send stuff to me. I tell you this because the exam, the mid-semester comes fast. You're doing your tutorials, you're doing your tutorials, you're doing your tutorials, you're like, I didn't quite get that, where's my work solutions? I can't work. If you are studying enough to know that you're having problems, please get in touch with us, we're here to help you. Okay, thanks.